Hello everyone and welcome back to A Plus Physics. I'm Dan Fullerton, and today what I'd like to do is take the 2016 AP Physics 1 exam and look at the free response problems from that test. Let's see if we can't solve them. Now as we go through this exercise, as we're making the video, the scoring guide for the exam has not yet been released. So quite probable that I might miss a point or two or do something silly somewhere in here. May not be 100% accurate, but at least it'll give you a good idea of the general gist of some of these problems. So with that, why don't we dive into free response question number 1. Wooden wheel of mass m with the rim with the spokes rolls down a ramp with some angle theta to the horizontal. The ramp exerts a force of static friction, so what we have is rolling without slipping. And the first thing they ask us to do is basically to make a free body diagram in part A1. So what I'll do is I'm just going to draw my ramp on here quickly. And we'll add our wheel to it. Might have to move that a little bit, but I think we should be able to do that. There's our wheel. And now we're going to draw the free body diagram. Okay, forces acting on our wheel. Well, the easy, obvious one is the weight, the force of gravity on our wheel, which acts at the center of mass, is going to be straight down, capital mg. We also have a normal force, and that acts at the point of contact. It is perpendicular to the ramp, so I would draw that probably something kind of like that. There's our normal force. And we have the force of static friction, which acts at the point of contact and is opposing the motion of the wheel. So there's the force of static friction up the ramp. So that would be my free body diagram for this problem. All right, now as we do this, it then says, as the wheel rolls down the ramp, which force causes a change in the angular velocity of the wheel? Well, changing the angular velocity, that's really an angular acceleration. And what causes angular accelerations? Torques. So there must be something here causing a net torque on our wheel. And as I look at the forces, the only one here that's causing a net torque is the force of static friction. So for part A2, I would probably say something like the static frictional force causes an angular acceleration because it is applying a net torque to the wheel. And you could put that out in writing. We're going to save ourselves a little time on the video. I imagine you guys don't want to sit and wait while I write all these out. So we'll just talk through the explain sorts of questions. Now for part B, it says for this ramp angle, the force of friction exerted on the wheel is less than the maximum possible static friction force. All right, I'm not sure that really helps me with the problem, but okay. What it does tell us is the magnitude of the force of static friction on the wheel is 40% of the force that's directed opposite the force of friction, or down the ramp. That allows us to write something useful. As I look at this, here's my free body diagram, but I notice that if I were to create my axes, I would probably make down the ramp my positive x, and I would make perpendicular to the ramp my y direction. Now, mg, the weight, does not line up with one of these axes. So I could create a pseudo free body diagram where I've broken all these up into their components. But this one's pretty straightforward. I can save myself some time because I know that the component of an object's weight down a ramp is mg sine theta. So the first thing I can do is I can write, based on the equation that they just talked about in the problem, that the force of static friction is equal to 40% of the component of the force pulling the wheel down the ramp, mg sine theta. So that piece should help me with basically solving for the linear acceleration, which sounds like a Newton's second law sort of problem. So next, I would probably write that the net force in the x direction is equal to the mass times the acceleration in the x direction. Well, what's the force pulling it down the ramp? That's going to be mg sine theta, and up the ramp minus our force of static friction, which we know is 0.4 mg sine theta. So minus 0.4 mg sine theta equals ma, and of course a is in the x direction. So now all I have to do is solve for the acceleration. The acceleration then is going to be, well, mg sine theta minus 0.4 mg sine theta is 0.6 mg sine theta divided by m, or I'm left with an acceleration of 0.6 g sine theta. Looks like it's independent of mass, which we might have predicted before we started. So that gets us through part B. Now, in part C, it talks about a second experiment on the same ramp where they have a block of ice with the same mass released from rest at the same instant the wheel is released from rest, and from the same height, and it slides down the ramp with negligible friction, so ignoring friction on this block of ice. Which object reaches the bottom of the ramp with the greatest speed? Well, let me flip to another page here so we have ourselves a little bit more room. And as I do this, as we think about C, which one makes it down first? Well, that's got to be the block. And there's a couple ways we could look at reasoning how we got this, how we know it's the block. In terms of forces, the way I would talk about it is that the block experiences no frictional forces. So there's nothing impeding the block going down the ramp. It has mg sine theta pulling it down the ramp, but nothing frictional. The wheel has mg sine theta pulling it down the ramp, but it has the force of static friction, 0.4 mg sine theta, pulling it up the ramp. So only 0.6 g sine theta accelerates the wheel down the ramp. Therefore, the block has a larger force on it. For the same mass, you end up with a larger acceleration. It'll reach the bottom of the ramp first. Now, for part C2, it wants us to explain the same answer again, but reasoning in terms of energy. And we could do the same thing there too. If we think about it, at the top of the ramp, both objects have gravitational potential energy. At the bottom of the ramp, that gravitational potential energy has turned into kinetic energy. Now for the block, all of that kinetic energy down at the bottom is translational. It's not rotating at all. For the wheel, it has some rotational kinetic energy and some translational kinetic energy. So all of that gravitational potential energy, which is the same for both, 100% of it becomes translational kinetic energy for the block. Less than that becomes the translational kinetic energy for the wheel because some is taken up by the rotational kinetic energy. So again, it has more translational kinetic energy for the block at the bottom, therefore it would have reached that first. So that's how I would go about answering question number 1. Let's move on and take a look at question number 2. All right, looking here at 2. What we're going to do is take a look at a new kind of toy ball that supposedly bounces perfectly elastically off hard surfaces. Okay, that's a little bit strange. Pretty certain that can't happen, but let's follow along. The student suspects that no collision can be perfectly elastic. Oh, they must have done well in physics. They hypothesize that the collisions are very close to being perfectly elastic for low-speed collisions, but that they deviate more and more from perfectly elastic as the collision speed increases. We're to design an experiment to test the student's hypothesis about collisions of the ball with the hard surface. And we have basic school laboratory physics equipment. Although I really don't think this is going to take a whole lot in terms of equipment. What would we do? A. What quantities would be measured? Well, what I would probably measure, I would take the ball, I would drop it from various heights, and I would measure the height to which it comes back up. So I'd probably use something like a video camera to videotape, I guess it's not videotape in most cameras now, but to record video of the ball being dropped and coming back up. I would pause it at its highest points and have a meter stick in the background, or 2-meter stick, or tape measure, something to measure the height off the floor, so that we could very accurately get the drop height and the maximum rebound height. So that's the equipment I would use, or what the quantities I'd measured would be the drop height and the rebound height. What equipment would I use? The video camera and the tape measure, and I just described how we would do that. Now, what's the procedure used to test the student's hypothesis and give enough detail so another student could replicate the experiment? Well, I'd probably start a couple centimeters off the floor and do this, a couple more centimeters, and do a bunch of data points until I'm probably up closing in on the height of whatever room I'm in. See what that looked like for data. So get a bunch of data points of drop heights and rebound heights using this method. Once I have all that data, Part B, how would I represent the data in a graph or a table? Well, what I would probably look at doing, I like to have a bunch of data in my graphs, and I love Excel or other spreadsheets for this, is I would probably have a column for drop height, putting everything in meters, of course, gravitational potential energy of the drop, which is just going to be the mass of the ball times the acceleration due to gravity at that point, times the drop height, so that's just mgh. I'd have the incident kinetic energy, the kinetic energy of the ball the instant before it hits the ground, which should be the exact same as the gravitational potential energy, assuming we neglect air resistance. And it says on our formula sheet, in all cases, we can assume air resistance is negligible unless it tells us otherwise. And it doesn't tell us otherwise, so I'd make that assumption. I'd also then have a column for rebound height. I'd have a column for gravitational potential energy on the rebound. And I'd have a column for kinetic energy on the rebound, which should be the same as the gravitational potential energy if this is the kinetic energy right after it hits the ground and it just begins its path back up. So these would be rebound quantities. These would be drop or incident quantities, however you wanted to phrase it. So I'd make a table of that information. And very shortly thereafter, I would probably look at graphing it. So how would we use that representation to determine whether the data are consistent with the student's hypothesis? Well, if we then graph our rebound kinetic energy as a function of the incident kinetic energy, we should see a slope of 1. They should be exactly equal for a perfectly elastic collision, a straight line. However, if the student's hypothesis is correct, we're going to see something kind of like that. It's going to tail off, and our rebound height isn't going to be as great as our incident height. Our rebound kinetic energy won't be as great as our incident kinetic energy, especially as we get to higher energies or higher heights. And you could have done this with drop heights as well, or gravitational potential energies. Lots of ways you could do this graph, but you should get the same basic shape, and you're really looking at the same concept regardless of which path you choose. So then let's take a look here at C. The student carries out the experiment and analysis that we talked about, must be a good student, immediately concludes something went wrong in the experiment because the graph or table shows behavior that is elastic for low-speed collisions, but appears to violate a basic physics principle for a high-speed collision. State a principle. Well, give an example of the graph that would show this. Well, you could take the same basic graph here, and if you saw elastic collisions, slope of 1, but you started to see it come up, this would be violating conservation of energy. You have more energy in the system than when you started, which shouldn't be the case because we're not adding any energy to the system. At least we don't think we are. So part 2 then says, state the physics principle that would appear to be violated. I would say conservation of mechanical energy. And the reason, because we have more energy out than we have in, and this is supposed to be a closed system, at least the way we're looking at it and given the assumptions that we're making. So that's how I would probably go about answering number 2. Let's take a break for just a second and we'll come back and do number 3. All right, and we're back with question number 3. This one's a bit more involved and a bit more of a unique transfer problem, let's put it that way. Not the standard sort of problem you'd expect to see. So I imagine this probably threw a lot of people for a loop as they took the exam. They give you a long track at some angle theta to the horizontal with speed bumps on it that are set distance d apart. Fairly long track with 100 bumps. We release a cart of mass m at the top of the track. Notice that after reaching the 40th bump, the cart's average speed between successive bumps no longer increases, reaching a maximum value that we call V average. So the time interval from one bump to the next after bump 40 becomes constant. We're supposed to consider the car's motion between bump 41 and 44 and see if we can't sketch a graph of velocity as a function of time from the moment it reaches bump 41 until it hits 44. So we've got a graph that looks kind of like this. Okay, so that's what our graph looks like. How would I sketch what's going on here? Well, to my mind, this looks kind of like a sawtooth graph. So I would take a look and say, is it right after 41? It's at its lowest speed compared to on all of the rest of the subsequent bumps. It's going to increase linearly until it hits 42. Once it hits 42, that's going to apply a force that slows the cart down. We're going to come back to where we start, and we're just going to keep doing the same thing. So you end up with this sawtooth pattern for the graph. So that's what I would look like there. Over the same interval, draw a dashed horizontal line at v equals v average and label it v average. All right, well, I would do the same basic thing between the minimum and the maximum here. I'll try my best to get right in between the two, but that should be in the middle. We have v average. So that to me would answer part A of question 3 in a great manner. Now, suppose the distance between the bumps is increased, but everything else stays the same. So the bumps are further apart. Is the maximum speed of the cart now greater than, less than, or the same, and why? Well, as I look at part B, I start to think that it has more time to accelerate between the bumps, so it's going to have a faster speed prior to hitting the next bump. It'll take a larger force to return the cart to its prior speed, so overall the cart must be going faster. So I would answer greater than, and give an explanation that says basically the graph has more time to accelerate before it drops down. Therefore, it's going to be going faster, and it'll take more force, so it's going to happen later on down the line. Part C. With the bumps returned to that original spacing, D, the track is tilted to a greater angle. What happens to the maximum speed of the cart now, and why? Well, again, I think this qualifies as greater than, which is probably pretty intuitive, pretty obvious. But why? How do you explain it? Well, these lines now will have a greater slope, same distance apart, at least distance-wise, not time-wise, but they'll have a greater slope because you have more of the force of gravity pulling it down the ramp. So more force is required to reduce the speed back to the initial one after each one once it hits this steady state repeating pattern. Therefore, the cart must be going faster again. Now, for part D. Before deriving an equation for a quantity such as V average, it can be useful to come up with an equation that is intuitively expected to be true. All right, I can buy that. That way, the derivation can be checked later to see if it makes sense physically. A student comes up with the following equation for the cart's maximum speed, where they say that the average speed is equal to some constant c times mg sine theta, the component of the cart's weight pulling it down the ramp, divided by d. Starting to notice a lot of ramp problems on this exam. Definitely a trend here. And c is a positive constant. And then to test that motion, they run this a few times, show us the average speed as a function of mass, and they plot that. And the question they ask then, is the data consistent with the student's equation? And this one I would answer very quickly without going into a whole lot of depth. You can take a look at the graph that they give you and notice that the y-intercept on their graph is not 0. The line does not go through 0 on the y-axis. So I would say no, it's not consistent. If this is an equation of the line, y equals mx, m being the slope, your x coordinate variable is mass, c g sine theta over d would be your slope, but you should have a plus b to cover the y-intercept if it's not 0. There isn't one, so I would say no, it's not consistent because there is a y-intercept on the graph. Would need to have more to that equation. And you could look in depth in a couple other ways and find that there's a little bit more that's probably wrong with this. But that would be the nice, quick, easy way, and since we're pressed for time on these sorts of exams, I'd stop right there and go on to part D2. Another student, it says, suggests that whether or not the data above are consistent with the equation could be incorrect for other reasons. Does the equation make physical sense? Well, to that part, I would also say no. As we look at this equation, As the distance, the spacing between the bumps goes up, we would expect the average speed to go down according to the equation, but that's counterintuitive to what we just said in part B. So the fact that as d goes up, v goes down, I would say tells you that something else is wrong. So both of these would be no sorts of answers. The explanation, the reasoning is a little bit different for each one though. And that gets you through question number 3. Let's take a quick break. We'll come back to number 4. All right, welcome back. We're going to take a look at question 4 from the free response exam, a fairly basic, straightforward circuit problem, where we have 4 identical resistors in the configuration shown. A and D in series, B and C in parallel with each other, but those 2 then in series with A and D. Find the potential difference across each resistor from greatest to least. Well, what I'm going to do is I'm going to redraw the circuit for just a second in a way that makes a little bit more intuitive sense to me. There's A, B, C, D. Same circuit, just drawn a little differently. Now, as I look at this right now, using Ohm's law, our current flow, our total current through this is going to be V over R. Where our resistance, if this is R and this is R, we've got 2R, they're in series, they add, plus the equivalent of these 2 in parallel, which is R over 2. So we would have a total equivalent resistance of 2.5R. So that's the current going through A, through D, and it splits between B and C. So that means if this is V over 2.5R is your current through A, and D, what you have going through B and C would be half of that, or current is equal to V over 5R there. Now, the potential drop across each of these resistors we can find by Ohm's law, current times resistance. Current times resistance here is going to be the same as current times resistance there, so VA and VD have to be equal. You have half the current through B and C with the same resistance through each of those, so that's going to be greater than VB, which is equal to VC. And we've answered question A. Well, part A, I suppose, with an explanation. Now, for part B, same basic idea, but we're going to remove resistor B from our circuit. So now our circuit basically looks like A, C, D. A nice, happy little series circuit. When resistor B is removed, does the current through A increase, decrease, or remain the same? Well, our total current now is going to be V over our total resistance, which is 3R. We just add up resistors in series. This is less than what we had up here. So what happened? It decreased, and we just explained why. Now for part C, it's now asking what happens when resistor B is removed. What happens to the current through resistor C? Well, what happens to current through resistor C? Right now the current through resistor C, when we've removed B, is V over 3R. Up here we had V over 5R. So really what happened is the current increased. It was V over 5R to V over 3R. And I'd probably put a few more words around this so that as you explain your reasoning, but we talked through it as we went through the problem, so no use spending more time on that here as you guys just watch me write. And with that, we can move on to question 5. Number 5, another one of those weird little problems that you didn't really expect to see on an exam like this. What we have is a uniform rope hanging vertically from an oscillator that's turned off. When the oscillator's on, it oscillates at a set frequency. The rope forms the standing wave shown on the right, and P and Q, which it shows you there, are points on the wave. For part A, it says the tension at point P is greater than the tension at point Q. Why? Well, as I look at that, this is more of a common sense sort of question. point P has to hold more of the rope than point Q does. Point Q only has to support the weight of the rope at that point and down below it due to gravity. Point B has to support all that extra rope. So I would put something in the answer there around the idea that more of the weight of the rope is held at P than at Q. Therefore, you've got more force on it, you've got more tension. And for part B, a student hypothesizes that increasing the tension in the rope increases the speed at which waves travel along a rope. In a paragraph length response that can contain figures, equations, things like that, explain why the standing wave shown above supports that hypothesis. And you can see that as you get lower on the rope, you have a shorter wavelength and you have more amplitude. So you probably want to bring something into your answer that includes that. I said something about this being consistent with the wave equation. Speed of the wave is equal to its frequency times its wavelength. If frequency is constant, set by the oscillator, we find that with a larger wavelength at the top of the rope, you must have a higher velocity, which is also where we said there's more tension, there's more force. So it's consistent in that manner. If lambda is bigger at the top and F is constant, V must be greater at the top, where tension is higher. So that would sufficiently answer 5B to my way of thinking. And with that, we finished the 2016 AP Physics 1 free response section. Thanks so much, everyone, and make it a great day.